Hello, everyone. All right, so today we're going to be talking about some clean core methodology for machining. And the first file we're going to work with is a DNA strand, which is a signature part. Before we get started, I'm going to tell you a little bit about myself. I recently joined the CNC software team as a technical content developer and trainer. I work remotely from my home office in Texas. I've been at Mastercam now for approximately 4 months, so I'm relatively new. Prior to that, for about 8 years, I've held positions in manufacturing as a CNC machinist, a Mastercam programmer, and process engineer for companies that develop products in tool and die, radiation testing, oil field servicing, and high performance automation. I have experience in 2D and 3D milling, multi-axis milling, robotics. Where I worked before, we had a lot of robotic welders that I programmed. Also, I have experience in lathe, wire EDM, and some post-processor modification. Before transitioning into manufacturing, I taught technology applications at the secondary level. So joining me today is Dylan, and he's a corporate applications engineer at CNC Software. And he's been working with Mastercam for quite some time. He's an expert in multi-axis and will be assisting during the webinar. Okay, so like I said before, we're going to talk about clean core programming. So I'm going to open up this DNA strand part. Okay, and I have several toolpaths, and we're going to recreate these. So let me just make a new toolpath group. Okay, and the first toolpath we're going to create, we're just going to follow the part surfaces and see what happens. So under toolpaths, we're just going to create a parallel toolpath. And we're going to use a 1/4 inch ball nosed end mill. For cut pattern, we're going to use a constant Z strategy. And for drive surfaces, we're going to select these outer surfaces of our helix. Okay. In addition to some slot covering surfaces that we've created. So we're avoiding the top and the bottom because we just want to machine the side of this part. For tool axis control, we're going to simplify things and use a 4-axis strategy. And make sure our direction is correct, Z-axis. And what we're going to do here is apply a 20-degree locked angle in the 5th in order to avoid contact with the center of the ball end mill. And also provide additional clearance between the spindle and the rotary table. So let's click OK. Make sure we don't have any collision control strategies enabled. And take a look at our toolpath here. All right, so let's backplot it. And I'll do a top view. So right now we're pointing at the tool based on the normals of the helix surfaces. So when we reach the sharp corners of the part, we have to wait for the C-axis to rotate 90 degrees at a time before we start back into the cut. So you can see what's happening here. It's rotating a full 90 before making the next cut. Which is going to result in long machining time and the probability of a not so good surface finish. So we want to address that. So now we're going to get to the secret here using the clean core method for multi-axis tool path creation. The idea behind clean core methodology is to generate your toolpath on a simplified version or a clean core of the geometry, and then to offset your toolpath to the actual surface you're trying to cut. And what this allows you to do is to take all of the benefits of the smooth tool control generated on clean core surface and carry them through the finished shape. So I'm going to create a copy of this toolpath here by right-clicking and dragging and choosing copy after. And let's go into the parameters. Now under cut pattern, I'm going to eliminate these drive surfaces. And we're going to drive this off of level 3, which is this elliptical helix we've created, which is a simplified version of the geometry we're machining. I'm going to leave tool axis control alone, but we're going to apply a collision control strategy here. So we're going to retract along tool axis, check against the flute. We're going to leave 0 stock. And for our check surfaces, we're going to select our part. In addition to the slots. And let's regenerate. So let's compare these motions here. Here's our first one. Okay, you can see this linear movement taking place on the edges, which is that complete 90-degree rotation, transitioning along the outside of the part. And with a clean core strategy, you see what happens. We have a much smoother transition, which is going to result in shorter cycle times and a better surface finish. So Mastercam prefers simplified geometry. What's happening is our tool axis is following this elliptical shape versus relying on the part surfaces themselves. So I want to show you something else here. If we didn't create this elliptical helix, something else you could do is create your own part. So I have level 1 selected and isolated. And what I'll do is just select it. And I'm going to copy it to a new level. 300's fine. I'll call this new part. And we'll go into model preparation and choose modify feature. And what I'm going to do is remove all these cutouts. So if I double click on each cutout, it should select all the faces because that's a feature within the solid. And double clicking allows you to select a feature. And then I'm just going to press enter. And you can see that that removed those cutouts. Another thing I want to show you, and the solid generation and modification in Mastercam has evolved quite a bit over the years. So if we do a push-pull on this part, and the reason I want to do this is to extend my toolpath motion, that way it machines the part completely. I'm going to pull this up And you see if I pull it up to infinity, it's making a replica of the part, right? And in this case, I'm just going to extend it 50 thousandths, press enter, and I'm going to do the same thing to the bottom. So I'm going to apply my changes and extend this out 50 thousandths. Okay. So let's go back into toolpaths. And I just created a copy of our previous one. Now, if we just eliminate collision control completely, under cut pattern, we're going to follow these surfaces. So this is our result, which you can see is similar to the initial shape. So we have this 90-degree motion taking place at each corner. So if we go back into solids, you have this constant fillet option. And what I'll do is select the edges we want to create fillets on to eliminate this linear movement that's taking place in the corners. And we'll make a radius of 0.08. Click OK. Regenerate. Okay, so now we have much smoother motion taking place. Now to apply a clean core strategy to the solid we just created, we need to go into collision control and enable it, and then establish our check surfaces. So our part, we'll select these outer surfaces in addition to the slots. So I'm going to right click on level 2, select all entities, and selection. But we're following this modified clean core, which wasn't elliptical. What we're following here is this part where we added the fillets and created a 50 thousandths extension on the top and the bottom. So this is what we're following for our cut pattern, and we're compensating to the part itself. So okay, so what I want to show you now is a different part with a different type of clean core strategy. With clean core, you're not limited to having your drive geometry on the inside of your part. So we call this clean core, core meaning the inside, but you can actually create surface geometry on the outside to drive your toolpath. So I'm going to open up this pumpkin example file. And I'll create a new toolpath group. And the first thing we're going to do is create a parallel toolpath using only the surfaces of the part. So no clean core strategy. We're going to use a constant Z machining method. For our drive surfaces, we're going to choose the pumpkin and eliminate this fixture geometry here. Tool axis control, surface with tilt, and no collision control strategy. Okay, so here's our result. I'll backplot it. All right, so we're machining the top of the part, and we come down and we have some irregular toolpath motion taking place, especially there on the very top. And then it sort of gets better as it moves to the bottom. So let's create a copy of this. And dive into the parameters. And let's use a clean core strategy. So I'm going to eliminate these drive surfaces. And then under levels, I have this lampshade style surface that's been created. But instead of being inside of the part, it's outside of the part. So I'm going to select it. That's going to be my cut pattern. Drive surface. Tool axis control, I'll leave it the same, but this time we're going to apply 2 collision control strategies. So the first one, let's retract the tool along the tool axis, and we're just going to check against the flute. And for surfaces, I'm going to triple click that pumpkin and then eliminate the fixture surfaces. And for stock to leave, we're leaving 0 because that's the geometry we want to actually machine. Now for the second strategy, I'm going to select the fixture geometry. And let's leave 0.010 of an inch. We're also going to retract along the tool axis. So I want to show you this. We have these options number 1 and 2 that show up when we apply collision control strategies. If you check this box that says drop tool wherever needed, this allows you to create a clean core surface on the outside of your part, and you're allowed to move your tool path into where the geometry is that you want to machine. So when we say quote unquote clean core, when you think of a core, it needs to be on the inside, right? You can actually create a clean core simplified model outside of your part and then use this option to move your tool down to the surfaces you're compensating against. So for this initial strategy, let's drop it down wherever needed and remove areas where it fails. For the second one, let's leave everything unchecked. We just want to avoid making contact with these surfaces. Let's click OK and take a look at our toolpath here. All right, so this was our first toolpath. And like I said, we have some irregular motion at the top because we're using these complex surfaces to drive it. And this is our second toolpath, which is much better because we're using this clean core strategy. All right, I had a couple other things I wanted to talk about, but it looks like we're running out of time. So if any of you have questions about what I've covered so far, please enter them in the chat and we will attempt to answer them. So.
Yeah, so one of the questions, Jeremy, was how you extended the core surfaces on the DNA helix, but not the part itself. And is it recommended that we extend as well? And
It's probably not a bad idea, but you probably have a better answer than me.
So I would say that depends on what you're doing. Since what we're doing with the clean core is all we're doing with the collision control strategy is changing the location of the points that exist on the clean core surface. So in this case, we're retracting them outwards to the final shape. So the extents of the clean core surface determine the extents of the final tool path at an approximate level. So we can extend or shorten the clean core shape to trim our tool path to the areas that we want without using a collision control strategy to do so. So in this case, Jeremy had lengthened the top of the DNA helix, so it had somewhat of a lead in to the actual part, which might not be necessary in real life, but just showing how if we modify the clean core surface, we're automatically modifying the final tool path result that we get.
Yeah,
And
so I guess to answer that, if we don't modify the size of the model, is there a tendency for the using the clean core model, even though it's been extended, to machine the top of the part and not provide an adequate lead in, lead out strategy, or not, as far as the extension? Because I mean, it looks like it worked out without having to modify the model, but there's a question I had.
right, I think that depends on your goals with the tool path. You know, for example, with the pumpkin, we had, you know, this lampshade that encompasses basically the entire height of the part, but we could also shorten that lampshade surface and just target the stem area of the pumpkin, for example. So that's one of the challenges of setting up the clean core is how you control the extents. And in a case like this, it's pretty simple because we have a part that has clear start and end extents. But if this were a blade with a root fillet, for example, we would have some more problems to solve down in the root area of the blade in terms of how do we want to terminate the path at the end. And this is where you would start modifying the clean core extents to drive what you want in the finished path.
Yeah, so you can see the difference here. Here's the initial modified clean core, which wasn't looking at this newly extended model, and you can see it would cut into it. And then I went ahead and modified the model we're going to machine. So I don't think it's a bad idea to extend the model in addition to the clean core to avoid collision, because you might have some unwanted toolpath motion. It could possibly, machine the top of the part versus remaining on the side. So definitely not a bad idea to create that extension in both areas.
So Samuel says, I'm glad you guys touched upon turbine blades in reference to clean core. I've run into issues employing clean core methodology on that. Jeremy, I think you've got an example that we won't program, but we'll show here.
Let me open up this file.
And this is a good example of where traditional inner clean core would fail, right? So this is actually not the cleanest model in the world, and we've got a very complex blade shape, compound shape that comes to almost knife edges at the end. And so if we actually path this, the vectors aren't great, and the tool transition motion over these lead and trail edge knife edges is not the best. And if we actually plotted out the vectors, you'd see them, jumping up and down vertically as well as we transition across these knife edges. So in a case like this, we'd want to do some sort of clean core motion, right, to clean up the vectors. But it's very, very difficult to draw a shape inside of this blade. So by using that dropping strategy and drawing kind of like a curtain that's around the blade, something like that, we can project our clean core inwards and get the same motion benefits. So now we've completely sidestepped some of the problems we have with the transitions over these bad surfaces on the lead and trail edge with this kind of method. And this is where you can actually see down at the bottom. Now we start to have choices though of what do we do in the fillet area of the blade, and maybe we start using trim and relink strategies or handling that differently. You know, especially for coming close to a 1-to-1 with tool shape. So Sergio says, is there a tutorial about this topic in Mastercam tutorials? There is not a tutorial specifically about this, a written tutorial. There are YouTube videos on our Mastercam channel that go over clean programming. There's also file examples on the Tech Exchange. Never been to the Tech Exchange. It's on the Mastercam site if you log in, and there's a drop-down link for Tech Exchange. And this is where we put all of our programmed part file examples that the applications group goes through. So there's a lot of high-end examples on things like clean core programming or multi-axis programming, blade expert, port expert, that kind of thing. So I will throw a link to that in the chat in just a moment.
Okay, yeah, so we just wanted to point out that you do have this capability here under collision control with additional strategies. And you don't necessarily have to retract along the tool axis. You could choose along surface normal, and you still have these same projection options. They're just worded a little differently. So if you change your strategy to along surface normal, we have project tool on direction wherever needed and remove areas where tool drop fails. You also have these filtering options, move tool outwards wherever needed or project tool inward wherever needed. If you wanted to filter the distance either outward or inward based on the collision control geometry that's selected. So if we choose that and regenerate, and I'll turn off my everything but the blade. So this would be our result. So you don't necessarily have to retract along the tool axis. You have other options available as well.
So this is not a final path. There's still some motion deficiencies on that trailing edge, and that's where we go after changes to that lampshade curtain surface, our clean core, so that we could get the motion we want projected inwards to that blade shape. You know, being a knife edge blade like this is probably one of the most difficult scenarios you could come across in terms of trying to project the tool path to it in that area.
Yeah.
Did anyone have any other questions on this before we wrap up? Jason asks, for the instructors that are here, could we get the pumpkin file? Yes, it's a great Halloween example. It's actually on the Tech Exchange. I think it's one of our most popular parts on the Tech Exchange. And I'll see if I can also just include a direct link to that. But if not, I can get that to you. And this is a great example to show this kind of multi-axis programming on, because obviously we could do an inner clean core shape on this as well. But it'd be more difficult to draw, a sphere inside of this shape or a cylinder inside of this shape than it is to just draw, a big visible cylinder outside to do the clean core on. So both methods work here, unlike the blade where we're kind of forced to that outside shape.
Yes, so if you wanted to do an inside shape here, we could do a cylinder, and I'll just snap it to the origin. Let me change my view here so I'm constructing in the right plane. And we'll just make it 140 thousandths for the radius and drag it down to the base of our pumpkin shape. And we'll just click OK. So parallel, constant Z, drive surfaces, and we'll select, let me move this cylinder to a separate level. Let me recreate this actually. Just make level 1000 and cylinder. Just drag it down here. Click OK. Okay, that's better. And parameters, cut pattern, select this cylinder, tool axis control, leave it the same. For collision control, I believe we already have our check surfaces based on our pumpkin geometry and our fixtures, so I can leave all that alone. Now we're going to turn off this projection if it's turned on, which is not. So now if I just click OK, now this is a clean core strategy. We're not on the outside of the part. We're actually driving our cut pattern from the inside. And now something to keep in mind though, when you have smaller geometry, less points are created. So if you create geometry on the outside of your part, you're going to have more toolpath points, which is likely going to result in a more accurate toolpath. So this is driving it from the inside.
Just to expand on that, when you do clean core programming, all the points you're creating that make up that toolpath are created first on the clean core surface. So when you're using collision control to retract to your final surface or project to your final surface, you're not creating any new points for the toolpath. You're just changing the location of existing points. So if you create your toolpath on something small for a clean core surface, like that tiny cylinder inside of this pumpkin, and then you retract out to the OD of the pumpkin, you're going to have a very sparse point spacing because you're just projecting those original points in the cylinder. So whereas you may have 30, 50 points a pass when you're doing the inner cylinder, if we create the path first, outer lampshade, and then project it inwards, we might have a couple hundred points a pass that we're projecting into the pumpkin. So keep in mind that point spread when you have large disparities between your clean core shape and your final part shape when you're doing this kind of projection.
Okay.
And also, when
I was going to ask, so in the event that we're projecting outwards with a smaller core, would it be beneficial to tighten up the tolerance and surface quality to create more points?
So in that case, yeah, you could go to 1/10 of a thou cut tolerance.
Something like that. Okay.
But consider the scenario where you have a flat plane as a clean core instead of a cylinder. In the case of a flat plane, tightening the tolerance to a very small value won't create any more points because we don't need a tighter tolerance to travel across a flat plane. So in something like that, I might go after maximum distance and set a very small maximum distance between points in cut pattern to artificially boost the number of points I am initially creating that are available for the projection.
Okay.
Also, when we are talking about clean core programming, we have two tolerances that we really need to look at to think about what tolerance we're applying to the actual cut surface. So we have the cut tolerance, right? But then if we go into parameters on that, Jeremy, and we go into collision control, the final tolerance that we actually cut the surfaces of the part with becomes our collision control tolerance. The cut tolerance on the cut pattern page is the tolerance for the points we initially create on the clean core. So we could make that really tight, but if we project all those points out to the pumpkin with a very loose tolerance in collision control, the pumpkin surface is going to reflect that. It's not going to be a very good surface. So when we do this kind of clean core programming, our collision control tolerance really becomes our final cut tolerance that we end up using on the part because it is producing the part surface. In cases like this, the most common use is that the cut tolerance and the collision control tolerance should match each other.
Yeah, so here I made it huge. I made it 100 thousandths. And you can see it overcutting the geometry quite a bit. So we'll match it. I'll put 1/2 thousandth. And regenerate. Okay. Yeah, so that does have a profound impact on the toolpath generation. That collision control tolerance is very important.
So Umakan asked a question, is there any rule for toolpath tolerance should be equal to the check surface tolerance or smaller? So that's what I was kind of just speaking to, in that in probably 95% of cases, your collision control tolerance, your check surface tolerance should equal your cut tolerance, because that's going to be what essentially is the final cut tolerance. In some cases where we were talking about point density earlier, the cut tolerance might be a little smaller, but you always have to keep in mind that the collision control tolerance is your final tolerance on the actual part surface in this case. In typical collision control uses where we're just tilting away the tool or something like that, this isn't how we're generating the final part surface, so that tolerance matching the cut pattern tolerance matters much less in scenarios like that.